boy! Okay. Whew. Oh, Lord. Okay, no, calm down, calm down. This is what studying is for. It's all gonna be fine. Plus, this room has an eraser, so really nothing can go wrong. So tonight is going to be pretty much dedicated completely to physics. I am pushing my public policy studying until tomorrow because I need to get this down tonight. Because I have physics lecture tomorrow, and more information is going to be given to me on a silver platter tomorrow, and I need to be able to understand the information that has already been given me so that I'm not overwhelmed when I am given new information. So with that, tonight we're going to be talking about continuous charge distribution and Gauss's law. Two things that I have struggled a little bit to comprehend, but hopefully I should be able to augment my knowledge a bit tonight. So up until this point, we've been talking about electric fields in relation to point charges. If we have a point and a distance between that point and a charge, then we can find the electric field. But things aren't as simple as that. For example, we can have a charged rod. In this particular case, the rod has a charge Q. And say, for example, we want to find the electric field that is now at that point P. This thing can't be treated as a point charge. At least not if we want to be accurate. So we need to keep in mind that this entire thing is charged, so the entire thing is going to be affecting the electric field at point P. Before I go on, it is important to note that this is a pretty idealistic rod. It has zero thickness. We can basically think of it as a charged line. But this isn't the only continuous charge situation that we need to be worried about. Another linear situation that we can have is a infinitely thin charged hoop. The charge of the hoop is Q. So those two cases were linear. Now we're going to go into cases that relate to surface and area. We can have a charged plane and a charged disk. Our final two cases are in 3 dimensions. We can have a charged sphere and a charged cylinder. Now, distinguishing between all these cases is really important because we solve each of them in different ways. Solving linears are the simplest, solving 3Ds are the most complicated. I am going to try and go over all of them tonight. It is only 8:30, so I have a few hours. So the electric field at any point given in relation to a body of continuous charge is going to be given by this equation right here. Now, our variables are going to depend on which case we're dealing with, and I'll show you how. New room, but no time to complain. This one still is an eraser. So in this particular equation, the integral is to represent that we are adding up an infinite amount of infinitesimally small point charges. Ke is, of course, Coulomb's constant, as we recognize. dq is the change in charge over time. It'll allow us to integrate. R is the distance that the point we're trying to find the electric field at is from dq. And r hat is the direction in which the electric field will be pointed. So, let's take a look at the simplest example. So we have a rod here of length L that is placed on the x-axis, and the y-axis bisects it. So on one side of the x-axis you have L over 2, and on the other side you have negative L over 2. The rod is charged to Q. Resting on the y-axis we have a point arbitrarily placed. We'll call that point P. Our job is to find what the electric field is going to be at any point on the y-axis. And here's how we do that. So let's recall our integral. Right now we're going to take each and every single one of the variables that are part of this integral, and we're going to unravel to see what they mean so we can actually solve the problem. First, Coulomb's constant. It's Coulomb's constant. It hasn't changed, and it won't change. dq is an infinitesimally small charged slice of this rod. Like I said before, it is going to allow us to integrate, but there's another way that we can define dq. dq is also equal to lambda dl, since this is a rod. Lambda is the charge density. So you can imagine this like as we go along the rod, the denser the charge is, the more charge is going to be added up with the integral. And plus, Since we have this in DL now, that means we can set our bounds of integration as the length of the rod. We can break lambda down even further into Q over L. Like I said before, R is going to be the distance between the point we're looking at and DQ. Looking at this particular situation, we see that R forms a right triangle with the X and Y axes, so we can define R as the hypotenuse of this right triangle, and using Pythagorean theorem, we know that R is equal to the square root of x squared plus y squared. Lastly, we're looking for R hat. If you recall, R hat is the direction of the electric field for any DQ. We add up all these different R hats along the rod in order to get our final electric field. So we need to find the components of this R hat vector so that we can relate them to our integral. Because without this R hat vector, this thing doesn't have directionality, and electric fields do have directionality. A scalar is unacceptable. We only settle for vectors. I've extended the R hat vector to make it a little bit more clear, but the y-axis and R hat share an angle theta. And that angle theta is what will allow us to define R hat. We decompose the vector. So R hat for us is going to equal cosine theta I hat plus sine theta j hat. But this form is unacceptable because it is in terms of theta, and we aren't integrating in terms of theta, we're integrating in terms of x. So we need to be able to get these things into x. So we just use SOHCAHTOA to do that. So because of trig laws, we know that sine of theta is equal to opposite over hypotenuse, or x over the hypotenuse, and we know that cosine theta is equal to adjacent over the hypotenuse, or y over the hypotenuse. It's also important to remember that y isn't a variable here, it's actually a constant. It's how we define p in this situation, so that's something that I got confused on, but now I know. So, we've defined everything now. We've defined dq, we've defined r, and we've defined r hat. So let's set up our integral. Now originally this thing came a little bit out of nowhere for me, so I'm going to go through it for my sake. So we've carried a few things down from the base equation and added a few more of our own things. First of all, it's good to notice that Coulomb's constant is still there, hanging out, having a good time. Secondly, we have added in the bounds, and the bounds are going to go from negative L over 2 to positive L over 2. So we're going to be integrating along the rod, which makes sense. Secondly, I've changed dl to dx because we're going to be changing in the x direction. I have also added in q over L for lambda, q and L right there. I have also squared r. And finally, I substituted in for the r hat vector. So this integral may seem really daunting to pull off, but it actually isn't that bad as soon as you realize that everything in this part over here, besides the x squared plus y squared and the dx, are constants. So you can pull out all those constants to get a slightly less messy integral. Now, granted, this is still a very tricky integral to compute by hand. We were told that we would be provided a sheet of common integrals and what they were equivalent to on midterms and exams. So if I come up against a problem like this in the homework, I'm probably just going to use Wolfram Alpha. But still, the process of getting here is really important, and I'm so glad that I'm reviewing it right now. But if we were actually to run it through a calculator, this is the final answer we would get. Now notice, this is really cool that there is no I hat component. And intuitively, if you take a look at this, it makes sense. Because you have an infinite amount of electric field vectors depending on where you are on this bar. There's one there. There's one there. But since it's symmetrical, since this is a place where it is going to be symmetrical, every single time you have an x component in a force vector on this particular system, there is going to be another x component on the opposite end of the rod that is opposing it and canceling it out. The only direction in which we actually have an electric field is the y direction, and we found that. Now, lightning fast, we're going to use the same logic and apply it to other instances. We have a charged ring of radius a and a point that is x away from the center. What's the magnetic field at that point? We got our basic electric field equation. dq is the same lambda as our rod like before, except instead of dx, we have d theta. Plus, we're multiplying that times an r. dq is a very, very infinitesimally small slice of our ring. Any specific r is the distance between dq and the point P, while any specific r hat is the continuation of that line in vector form. Now first, a couple important things to notice. First of all, a and x are constant, so r is never going to change, so r will be a constant. Next, due to the symmetry of this object, the perpendicular forces are going to cancel out. Therefore, the dEy component is not going to exist because all of the forces are going to cancel out, so once again, we only have an x component here to deal with. Now here's the tricky thing. In order to do more work, we're going to need another angle. Because theta, remember, is the angle that we integrate along. So as we integrate along the hoop, theta will be increasing. The new angle alpha is the angle between the r hat vector and the x-axis. And using laws of similar triangles, we can also infer that the angle will be alpha here as well. So we know that r hat is going to be equal to cosine alpha I hat. Remember, there's no j hat component because all the j hat components cancel each other out over the integration. So we can effectively just ignore that due to symmetry. Also remember that we shouldn't be intimidated by alpha because it's a constant angle. If we were given real numbers for this, we could use trigonometry to find alpha. Now this seems really fast, but we have everything. And here's why. Previously, we needed to convert our I hat and j hat components from terms of theta into terms of x. Now this integral is in terms of theta, so we don't need to convert anything. We're just left with constants. So let's plug everything in. So with everything plugged in, our final integral is going to look like this. We have ke, as always. We have d theta from dq. We also have our lambda, which is q times r over L. Now the L is going to be the circumference of this hoop, which is, in this case, 2 pi a. And then we have r squared, which is, of course, the quantity of a squared plus x squared. Now, since we have an a in the numerator and in the denominator, we can cancel them out. Since everything left over here is a constant, we can pull it outside of the integral. When we're integrating this, since cosine alpha is technically a constant, we just tack theta onto the end. When we multiply this out, the 2 by here and the 2 by here cancel each other out, giving us this as our final answer. It's 10 o'clock.